Go until 10:15. I'll probably be a little bit shorter than that so that we don't wear everybody out at the very beginning. So,
I'm sorry, I had an announcement today. So these slides which are appearing here, we posted on the website. If you go to schedule, where the schedule is listed, the first few talks, there are links you can click. And so if you want to follow on your laptop the slides and maybe be a page ahead or a page behind, you're welcome to do that.
okay. So, what this conference, this workshop is about is the Atlas software project. The thing that we're maybe proudest of in the Atlas software project is that the software can take a real reductive group and any representation of this real reductive group and tell you whether that representation is unitary. So what we want to do in these 2 weeks is explain how you ask questions like that, and that's going to be the job of more or less everybody else. My job is to try to explain why such a question is interesting and what the mathematics is underneath the software. So all of the various lecture series are supposed to fit together and depend on each other, and it's completely fair if you have a question about something that I say to ask Jeff while he's talking. It's practically preferable. And in the same way, you know, if you have a detailed technical question about the software, you can ask me and I'll giggle or something. And we want everything to fit together. And most of all, we want you to have an idea of what's going on all the time in the lectures. A lot of times in math lectures, you're sort of only barely hanging on by your fingernails, hoping that when you look at your notes tonight with the book, you'll be able to figure out what was going on.
Does that happen to you too?
I listen to loose things. Yeah, it happens to me too. Actually, the very first class I took in graduate school, I'd signed up for a course from Singer about characteristic classes. And for the first lecture, Singer brought in Atiyah to talk about the history and motivation of characteristic classes. And Atiyah talked for an hour and a half, and I thought, oh, holy shit, what have I done? You know, I don't belong here. I can't possibly live in this environment. Turned out Singer was easier to understand than Atiyah. And in the same way, Jeff will be easier to understand than me. Just an analogy. But please ask questions. And I've planted some deliberate errors in the slides so that you can be sure to ask questions. Jeff already found the first error. The first slide said University of Massachusetts, Boston, 2012, but he cleverly noticed that this was not the University of Massachusetts in Boston, so that one's fixed. But ask questions. Okay, so what's the, oh dear. Why is this? Oh, no? Oh, I turned it off. Good. Okay. So, roughly speaking, the first topic here, the first lecture is labeled in the schedule as overview, and that's most of what I'll do in this topic one is this, why do people look at unitary representations? And I'll start talking about what the Langland's classification is, this number 2. This part 3 is probably mostly for tomorrow. Okay, so the basic question is, well, what's a group representation? And I think that this is something that all of you know, that a group representation means a homomorphism from a group to a general linear group. In other words, it's the same thing as an action of the group on a vector space by linear maps. And from the point of view that I want to think about, the main example is you have a group acting on some kind of space, not a vector space, X, and you make something like a space of functions on X. And since the group acts on X, it acts on functions on X, and you get in this way a representation. So what's a unitary representation? Well, I'll remind you that a Hilbert space means a complex vector space with a Hermitian form, which I write with angled brackets. And what being Hermitian means is it's not symmetric, but if you interchange the arguments, the value goes to its complex conjugate. And the form should be complex linear in the first variable, and because of this condition, it's conjugate linear in the second variable. If I put A W1 plus B W2, I get A bar V1 V W1 plus B bar V W2. The big assumption is that the form is positive, that if you pair any vector with itself, any non-zero vector with itself, you get a strictly positive number. And with that positivity, you can define a metric on the Hilbert space. The distance between two vectors is, you take the difference of the vectors and take the pairing of that thing with itself, you get a positive number, so it has a positive square root, and you define that to be the distance between the vectors. And the analytic part of the definition of a Hilbert space is that the Hilbert space is complete in that metric. That's what you need to do analysis. Completeness makes Cauchy sequences converge, so you can have a reasonable theory of limits and so on. So, okay, so a unitary representation, the definition looks just like the definition of a representation, except that now the vector space is required to have this extra structure of being a Hilbert space, and this, I put the letter U instead of GL. U means linear maps that preserve the inner product. So I should write that. So what that means is that,
David?
yes.
I think the blue might be better.
Blue is better. Not yet. I mean, yes, of course. But, well, in any analytic setting, the definition of a representation should have some continuity assumption. But for now, I've just written this algebraically. So the this is what a unitary operator on h pi means. Sorry, I shouldn't call it u, I should call it, sorry. I should call it t. Well, I've written this pretty badly. Anyway, yeah. So that's what a unitary representation is. So just as a representation is an action on vector space by linear maps, a unitary representation is an action by unitary linear maps. So just as the main example of a representation is you have an action on a space and you look at an action on functions on that space, the main way you get a Hilbert space is by starting with a measure space. So I've got an action of G on a space preserving some measure, and then using the measure I can define the space of square integrable functions, L2 of x, and the group then acts on these square integrable functions by unitary operators. Okay, so that's what the objects are. So here's what the sort of algebraist way of thinking about what harmonic analysis is. You have a group acting on some space, and you have questions about that space. So the way you should proceed is you should find a representation. What makes this hard is that a group acting on a set, there's no linear algebra. One of the most powerful kinds of mathematics there is linear algebra, and with a group acting on a set, there's no linear algebra. So you drag linear algebra in, you make a vector space of functions on x, and you find a way to rewrite your questions about x as questions about this vector space. The next thing you do is you try to write your vector space as a direct sum of G invariant pieces. And whatever you want to know about the big vector space becomes a question about each one of these pieces. And more or less, each of these pieces is supposed to be an irreducible representation of the group. So what you do is you try to understand all the irreducible representations of the group. And then what you know about all these irreducible representations, well, you understand each V row, you understand V, and therefore you've answered your questions about X. That's the idea. Gelfand had a more precise, better idea. And he said, if you've got a topological group acting on a space, then here's what you should do. You should attach to X not just any vector space, but a Hilbert space. And make your questions about X into questions about this Hilbert space. And then you should decompose the Hilbert space as a direct sum of nice G invariant Hilbert subspaces, and make your questions into questions about each of these pieces. So each piece, well, the pi and alpha are supposed to be the same. Each piece is an irreducible unitary representation of the group. So Gelfand said you should understand all the irreducible unitary representations of the group. that's called the unitary dual problem. And the things you know about these irreducible unitary representations then tell you things about your original X. So what we're going to talk about is this unitary dual problem. How do you understand the irreducible unitary representations of G?
Can you give a simple example of questions about X that could be effectively answered by this kind of approach?
Absolutely. So let's see. I had let me see if I can remember. So acting on this set X is the symmetric group. This is permutations of the cards. And a question you might ask is, what's the cardinality of X? And a way to answer it is to look at the space of functions on X, and then the answer is the cardinality of X is the dimension of this space of functions.
Any preferred field? It's true, I think, except in characteristics 2 and 13. Probably even there if you work harder. So that's, yeah, no, the field doesn't matter, but I'm in these talks always going to use vector spaces over C. That's the default. So how do you, well, you know that the irreducible representations of S52 correspond to partitions of 52. And I'm not going to remember this correctly. And what happens is that this V is a sum over all the irreducible representations of S52, irreducible representations pi of S52, with the property that pi restricted to S5 times S47 contains the trivial representation. So this is, I'm doing this badly, and I just wanted to know the
yeah.
example of the question, not before.
Yeah. But this, I mean, obviously this is a ridiculous example in many respects. But it's the shape of, this ridiculous, in this case it's a ridiculous way to solve the problem, but in other cases a less ridiculous way. I'll maybe yeah. let me, well, no, I'm not going to try to write another example now. Okay. What I want to say is, well, so I had these two pictures. I had this harmonic analysis for dummies, where you just used representations, and then Gelfand's version, where you use unitary representations. What's better about Gelfand's version? So that's an important question. So in order to make the slides have fewer words, I'm going to use this symbol for better. So the question is, why is it better to try to write a unitary representation as a direct sum of irreducible unitary representations? Why is that better than writing any representation as a direct sum of irreducible representations? So these decompositions in the two programs are very much like eigenspace decompositions for linear operators. So if you have a linear map on a vector space, you can try to find invariant subspaces for the linear map and take apart, well, ideally you try to find eigenspaces for the linear operator. And you try to write the vector space as a direct sum of eigenspaces. So what happens is that if you study the spectral theory of unitary operators on Hilbert spaces, that's a much more powerful and easier theory than the spectral theory of arbitrary linear operators on, say, topological vector spaces. So why are unitary operators easier? Well, if you have a Hilbert subspace that's preserved by a group action and closed, then the whole Hilbert space is automatically, you have this orthogonal decomposition. The big space is the subspace direct sum, the orthogonal complement. So in the world of vector spaces, there's nothing like orthogonal complement. If you're lucky, you can maybe prove that sometimes there exists a complement so that the space is a direct sum, but you'll never have a uniqueness theorem. And so if you have a group action, you know, your G invariant subspace will never hand you a complementary G invariant subspace. But using this easy fact that any closed invariant subspace has an orthogonal complement, just by soft analysis, you get what's called a direct integral decomposition. Under very weak hypotheses, any unitary representation of G decomposes as, well, a direct integral, not a direct sum, of irreducible representations with some multiplicities. So I'm not going to talk about that in detail. Maybe there will be some examples. Second reason that this unitary stuff is good is that there are lots of unitary representations. So it's not a terribly difficult thing to find spaces with G invariant measures on them. And so you get L2 spaces which are unitary representations of G. Third thing is that even if you have a question that doesn't appear to be about unitary representations, you can make it about unitary representations. So when you study differential operators on Rn, it's very helpful to understand the Schwartz space of functions. Well, here I wrote just R, but same thing on Rn. The definition of the Schwartz space doesn't have any Hilbert space in it. You want some bounds on derivatives of the function, but there's no L2 integrals. Nevertheless, it's true that the Fourier transform of the Schwartz space on Rn is the Schwartz space on Rn. And the Fourier transform is a unitary representation thing. So this statement is telling you something interesting about the Schwartz space using unitary representations. Okay. Well, so if unitary representations are the best thing, why do we pay any attention to non-unitary representations? The reason is that more or less, if you look at all the irreducible representations of some group, more or less that's a complex algebraic variety. Well, why is that? What I claim is that if you fix a complex vector space V, that the group homomorphisms from G to GLV are an algebraic variety. Well, the reason is that, if, for example, if the group has capital N generators, then what a group homomorphism from G to GLV is, well, it's an N tuple of matrices. You have to say where the generators of the group go under the representation. But then the relations of G have to be satisfied by these matrices. And that defines an algebraic condition in this algebraic variety. Well, that's why this thing looks sort of like an algebraic variety. And mathematics is full of very beautiful descriptions of algebraic varieties. And what we're going to find is that the Langlands classification is a beautiful description of all irreducible representations of this real reductive group. I think I never made a slide saying what a real reductive group was. So I'll just mention this briefly. So an algebraic group, well, you can think of as a subgroup of some GLNC defined by polynomial equations. And the matrix entries and the inverse of the determinant. And well, I'm not doing any of this carefully, but defined over R means that these defining equations can be taken with real coefficients. So an example, well, an example is NC, which is the defining equation is G times the transpose of G. It is the identity matrix, and so this is n squared quadratic equations in the entries of G. And these equations obviously have real coefficients. That's, I won't write them down, but that's clear enough. And then so I'm going to write, well, when you have these things, you get this group of real points. And well, this is just a group that's usually the compact orthogonal group. Okay, and so what we're always going to study is a complex connected reductive algebraic